Welcome back. We're going to get started on the last phase of discussion for stereoisomers. And we've already talked about enantiomers and diastereomers. While I gave practice problems for enantiomers, I did have practice problems, but I accidentally cut the video short. So I will give you example practice problems for diastereomers at the end of this video. So watch out for that. Now, one of the other things I've already mentioned while I talked about enantiomer and diastereomer is the idea of identical. Just as the name sounds, if the configuration for one molecule is exactly the same as the other, then it's identical. So without further delay, let's bring our table here and draw our carbon, which is chiral. And the first point of contact here is 1. So this is 2, this is 3, this is 4. So it's clockwise, right? Clockwise. And the minority group is in the back, so it's back. Clockwise back is R, so that's R. Let's do it for this one. 1, 2, 3, and 4. So it's 1, 2, 3. It's counterclockwise and it's back, so it's S. Now, what do we mean by front and back is the minority group, which is 4. Is it in the front or back position? So 1, again 2, 3, and 4. So that's again clockwise and back. That's again R. 1, 2, 3, and 4. So that's counterclockwise back, and that's S. So if you draw this is R and S, this is R and S. If configurations are identical, then that's identical, just as the name sounds. Okay, and here's the examples for diastereomers. Okay, and the last one I want to talk about is Meso. Okay, so let me go back. These are the practice problems for diastereomers. Okay, you can do it in this at the end of, you can do this as part of this my thoughts versus the previous one. Okay, all right, the last one is Meso. Okay, while a molecule contains chiral carbon, if it also contains a plane of symmetry. It's very important because there's so many explanations going around and it's very confusing. So I'm going to try and keep it very, very simple. What do I mean by plane of symmetry is, don't worry too much about whether it's in or out or whether it's, you know, front or back. Just look at the molecule itself. Does it look exactly the same if you cut it right in the middle, like right here? Yes, you need first chiral. That's a requirement for Meso. But on top of that, sometimes molecules have chiral carbons, but they don't necessarily have a perfect plane of symmetry. That is one side. So let's say, what I mean by that is, let's draw it without, you know, the front or back recognition. Okay, we're not so much worried about that right now. We've already used that to establish chirality and we're done. Right now, everything on this side is also on this side. Like I said, if you cut it right in the middle, this side has, whatever has is also on this side. So this has a plane of symmetry. Okay. So with that in mind, your compound can never be Meso. It must have two things. That is, it must not only have chiral carbons, the chiral carbons must be split by a plane of symmetry. But there's another important thing that's very, very important. We're going to solve that. So let's actually draw this one more time, except this time I am going to actually write it in this form. Okay. The chiral carbon is a key requirement for Meso, But that and plane of symmetry alone is not, there's actually a third condition, which is what we're trying to solve. So plane of symmetry is one, chiral carbon is a second, but the third condition, you can only get it if you actually know how to do R and S. So this is your first point of contact. So 1, 2, now priority is, this is always 4. So that's clockwise, right? Clockwise and back is R, right? Okay, let's do it for this side. So 1, this is always 4, this is 2, and this is 3. So this is counterclockwise and back, that's S, right? So for a compound to be meso, first you need to have chiral carbons, which we have established. Then there must be plane of symmetry, where we're not necessarily worried about the in-out. We just have to make sure that everything looks the same on both sides. So 2 conditions are met, right? Chiral is met, check. Plane of symmetry met, check. What about the 2 chiral carbons? Are they have same configuration? If they are the same, then it's not a meso. But in this case, we have R versus S. So yes, they have to be opposite. When all of this is met, that's a meso. You could have 2 more carbons on either side, but if you have RSS, then the other must be SRR. Does that make sense? So whatever you have on this side must be opposite on this side for it to be meso. Okay. If you do this, this has chiral carbon. Okay. Check. This has plane of symmetry. It sure does. So let's check that. Okay. What about R and S? Let's do it. So this is 1, because that's the highest priority group attached at the first point of contact. This is 2, this is 3, and this is 4. So that's 1, 2, 3. It's clockwise, right? Back is R, right? This is 1, 2, 3, and 4. You already guessed where I'm getting at with this. Counterclockwise, right? And front is S, right? No, counterclockwise front is also R, sorry. So we should have had R versus S, but that's not what we have. We have R versus R, so it fails the third condition. So that means not meso. Does that make sense? That's all I was trying to drive here. And I think I have, so I want you to practice this meso. Okay. Now, constitutional isomers, I mentioned, we've already learned this. Okay. Now, this is constitutional. RS, ZE, cis trans. Okay. All these are conformational isomers. Okay. They not only have same structure and same formulae, but they also have different arrangements. These are conformational isomers. This is constitutional because 1, 2, 3, 4, 5, 6, and 7, right? 1, 2, 3, 4, 5, 6, 7, right? And then we know our formula is CnH2n+2, right? So C7H16. This is also C7H16. And you don't see any of those in plane, out of plane stuff because this is, again, this is constitutional, same structure, different formulae. The conformation is not represented here, whereas R and S, Z and E, cis and trans, they're all conformational isomers. So I just want you to show there are 2 different subtle isomers. One is conformational, which is more stereochemistry oriented. Constitutional is almost just like same formula, different structures. All right, and that's all I had to say. So here's the practice on the meso, and I think that's all I want to say on the topic of stereochemistry. It may seem like less content, but if you understand it, it's very easy. If you don't understand it, then you need more practice and obviously my help, and then we'll get over the line. All right. So stay tuned for more videos.